So this is an introductory video to acids, bases, and salts. And we're going to have a series of videos where we break down the various types of problems associated with acids and bases. But right now we're going to look at just an introduction of what is an acid, what is a base, what are their definitions. There's lots of different definitions for acids and for bases. The traditional definition of an acid is that it's a chemical that's made up of hydrogen, and so that it begins with hydrogen. And that's what I want you to know as far as how to look at a chemical and go, oh, that's an acid. It always begins with hydrogen. And so if we were to look at these examples I've got over here, we can tell that HCl, which is hydrochloric acid, is an acid because it begins with H. HNO3, an acid because it begins with H. Now these are aqueous acids, which means that they're diluted down so that you mix so much of the acid with so much of the water to get the concentration of the acid that you need. The traditional definition of a base is that it has OH, which is hydroxide. So if we have the hydroxide, the OH, it is a base. Example, NaOH, we can tell a base because it has the OH. Now another word for base is alkaline. You've heard of alkaline batteries before. They're talking about what that component is on the pH scale, and it registers in that basic range. So some characteristics of acids versus bases. Acids have a sour taste. If you think of eating a lemon with that citric acid, bases have a bitter taste. If you, any of you've ever put soap in your mouth because you said an ugly word, or you put soap in your mouth just to see what it tastes like, bitter taste. Acids react with carbonates and they make CO2. Bases react with fats and they make soap. Acids react with metals to produce hydrogen gas. Bases do not react with metals. Acids turn litmus paper pink. Bases turn litmus paper blue. Bases blue. Acids and bases react together and they always make salt and water. And you're going to hear that one over and over again. Acids and bases mix together to make salt and water. Now the person that came up with this first definition of acids and bases was Arrhenius, and he said that acids could donate a hydrogen and bases would donate an OH. And so the acids begin with hydrogen and bases have OH. So here you have Arrhenius's definition of acid and base. Arrhenius says that an acid produces hydrogen in water, a base produces hydroxide in water. Now, if you will remember from when we did our nuclear chemistry, another word for hydrogen is proton, because hydrogen has that one proton. So Bronsted and Lowry revisited Arrhenius's acid-base definition, and they redefined acids and bases. So the Bronsted-Lowry definition of an acid is that it is a proton donor, meaning it can give up hydrogens, and that the Bronsted-Lowry definition of a base is that it is a proton acceptor, meaning it can accept a hydrogen. So looking at this example here, we can see that this right here is a Bronsted acid because it donates a hydrogen. And so it ultimately ends up like this here, missing the hydrogen. This right here is our Bronsted-Lowry base because it accepts the hydrogen, and you come over here and it's accepted that hydrogen. In this example here where we have ammonia reacting with water, the ammonia is going to be the base that accepts the hydrogen, and the water is going to be the acid that donates the hydrogen. So in addition to Arrhenius's traditional definition of acid and base and Bronsted and Lowry's definition of acid and base, we also have the conjugate acid and the conjugate base definitions. A conjugate acid is a compound that's formed when a base gains a hydrogen, and a conjugate base is formed when an acid loses a hydrogen. Now, when we look at conjugate acid and bases, this right here is a conjugate acid, and then notice that when we get over here, it has lost a hydrogen, so this is the conjugate base associated with the acid. Here we have the conjugate acid. Notice that it has one more hydrogen than the conjugate base, and that's how you tell a conjugate acid-base pair. Okay, so again, looking at how we would tell this, we have NH3, we have NH4. The one with the larger number of hydrogen is the conjugate acid. The one with the smaller number of hydrogens is the conjugate base. These two go together. When we look at this one and this one, the H2O has more hydrogens. It has one more hydrogen than the OH. So this is the conjugate acid. This is the conjugate base. Another definition of acids and bases is looking at the Lewis definition. Now, a Lewis acid is going to be defined as an electron pair acceptor. The Lewis base would be the electron pair donor. So if we look at this example here, we can see that the NH3 has these lone electrons right there. Okay, and then here we have the BF3, and you'll notice that when they come over here, they form a bond. In order for them to form a bond, this has to give an electron for this to match up. So because this one is giving up electrons, this is an electron donor, this is a Lewis base. Because this one right here is accepting the electron, this would be the Lewis acid. So just going over exactly what an acid is, on the pH scale going from 0 to 14, everything under 7 is a pH, everything with a pH less than 7 is an acid. It has hydrogen in it. It is corrosive with metals. It's a good conductor of electricity. An acid mixed with a base makes salt and water. Now, on the pH scale, the closer the acid is to 7, the weaker the acid is. The further from 7, the stronger the acid is. So an acid with a pH of 1 is much, much more acidic than an acid with a pH of, say, 5. Going back over again, acids are sour tasting. They're good conductors of electricity. They're corrosive. They react strongly with metals, and they turn litmus paper red. So some areas that you would see acids. Acetic acid is in vinegar. Vinegar is 3% acetic acid. Citric acid can be found in lemons and limes and oranges. A lot of times if you eat like lemon heads or Sour Patch kind of candy, citric acid is what is put in there to give it that sour taste. Ascorbic acid is vitamin C. Your body has to have that to function. Sulfuric acid is used in fertilizers, it's used in steel, it's used in paint, it's used in car batteries. Hydrochloric acid is stomach acid. If you ever want to know what acid tastes like, think of that time where you vomited and it's burned your throat. That's an acid burn. Another name for hydrochloric acid is muriatic acid. So you could go to a hardware store, go back, and you could buy muriatic acid. Sulfuric acid is found in car batteries. Nitric acid Nitric acid is found in explosives. It's also occasionally used in lab experiments. Acetic acid in vinegar. Carbonic acid is found in Cokes. You could take a chicken bone, you could put it in a Coke, come back in a week or two later, and the bone would be dissolved from the carbonic acid. You could do the same thing with phosphoric acid from sodas as well. Phosphoric acid is used in flavoring. Formic acid is the acid that is produced by ants, and when you get an ant sting, that's actually a burn from an acid. Now, this is just a lab reminder that when you mix an acid with water, it's very important to know the order. You always add acid to water, never water to acid. And that's because when you add acid to water, you're taking the water and you are slowly changing the pH to become more acidic. If you add water to acid, it changes the pH of the acid very quickly. It causes an exothermic reaction. That energy has to go somewhere, and that's going to force that acid to overflow, and it can shoot up. It can hit your arms, your legs, your face, your hands. Not a good thing. If you ever spill an acid on you in a lab, if you feel any kind of tingling sensation remaining after you've washed that area, then you need to go back and rinse more. That means that that acid is still burning your skin. Now, some acids are classified as strong acids and they ionize completely. They're strong electrolytes. And then some acids are weak acids and they don't ionize completely and they're weak electrolytes. And so you're going to have some homework assignments where you have to identify a strong acid from a weak acid. And there's really not any trick we can show you. It is kind of like a memorization. So what we're going to do is we're going to have you get your Fat Daddies out. We're going to have you pause the video and we're going to have you copy down the list of strong acids and weak acids. This is not all the acids that exist, but these will be the ones you will run across on your homework and on your lab activities. So these are the list of acids, the strong acids and the weak acids. And so what we need you to do is I need you to pause and I need you to write down these acids, these strong acids and weak acids, the formulas. Okay, and then when we look at acids, we can also classify the acids really based on how many hydrogens or protons are present. So if we look at these right across here, you're going to notice in this one, they only have one hydrogen. So if we have a chemical formula, it's an acid and there's only one hydrogen, we call that a monoprotic acid. This one, you'll notice that this is sulfuric acid. You'll notice that it has two hydrogen. This is a diprotic acid, meaning it could give up two hydrogens or two protons. If it has three hydrogens, we call that triprotic. And if it has more than one, we can just use a general term called polyprotic. So this could be polyprotic, this could be polyprotic as well.